Hello, good morning, everyone. Welcome to the Arcteq webinar Wednesday. The video you are watching now is the recorded one, and I will be available in the comment section to answer your questions. If you need any further help, you can reach us through the Arcteq support portal by reaching the Arcteq website. The topic for today's webinar is configuring and setting cable and differential protection. My name is Rajkumar, and I'm working as an application engineer with the technical support team of Arcteq. Let's go through the presentation. The contents for today's presentation are causes of the cable end faults. So here we will learn what are the reasons that causes the cable end faults, the working principle of the cable and differential protection, how this cable and differential protection is represented in the Arcteq relays, the block diagram, CT connections, and activate setting, where we will go through the activate software and we will learn how to do the settings. Then there is the differential characteristics, where we will learn how to plot the differential curve and what this curve means and what the parameters of each curve are represented there. Then we will see what are the benefits of this protection system, why we use this, and then we will go through the data sheet to see what are the limits, what are the parameters that we can set. And then there is this testing where I have an Omicron device connected with the relay, where we will do a short testing that how the relay operates with the differential currents. So the first slide says that the causes of cable end fault. Well, there are many reasons for the cable end faults, but the faults within the switchgear are typically caused by human errors, equipment failure, foreign objects or animals in the gear, or by combination of aging material, dirt, and lack of maintenance. Here, human errors refers to the commissioning team. We know that the cable end are most sophisticated part of the network that should be done in a proper way. Otherwise, it leads to the faults. The foreign objects refers to the animals. We know that substations are pretty far in the forests, and there is possibility that the wild animals could enter, such as snakes, mostly found in the switchgears. And obviously, lack of maintenance is also one of the main causes. Cable ends are the most vulnerable part of the network and a possible potential to the fault. We have always seen that there is a potential in the cable ends that leads to the fault if not detected timely. As per empirical data, the most common non-human intruded fault located in the cable compartment is especially the cable ends. Then, degrading of the insulation. With the time, when the cables get older, the small earth leakage faults start to flow through the cable ends, and it starts to damage the insulation because it starts to heat up the cable ends, and if not detected properly and timely, it could lead to the fault. The fault could be one cable end, and even if it's not stopped there, then it would lead to a cross-country fault. That's why we have such protection systems that detect the fault before to happen and proactively it stops it before happening it. What is the working principle? The working principle of this protection system is as similar as the differential protection normally used. It basically works on the Kirchhoff's current law, that we have a defined protection zone and current entering and leaving are added or subtracted depend upon the basis of how we have done the connections. So it adds the current flowing through each phase and then with the residual current. If there is a differential current, there is any difference, if there is any internal fault, there will be a differential current start to flow, and the summation of all these is not equal to 0, and that leads to the operation of this protection function. Here you can see in the picture, there is a one CT connected with the wire. That CT before the breaker is a residual CT. And then we have three CTs. Those CTs are with each phase. This is the common practice, and all the CTs are normally available in the network. Then this protection function, known as cable and differential, is represented as I0D87N in the Arcteq relays, and it has two operating modes. It operates as a restricted earth fault, and it also operates as a cable and differential. In today's webinar, we will focus on the cable and differential only. This particular protection function settings are done in a way that you can compensate the differences, the differential characteristics of the CT. For example, normally in the medium voltage, we use 5P class CT. There is possibility that the two CTs of the same size, same rating, from the same manufacturer, there can be the difference in the characteristic curve. And it has been seen practically that it stays from 0 to 10%. 10% is the maximum differential current that can happen in 5P class CT. So we have a possibility in this protection function, we can compensate the differential current. I will show you when we were doing the setting with the Activate software how to compensate this differential current. So we have an option there where we can do this natural unbalance equal to 0. This is the block diagram. Here you can see you have 3 phase currents. Those are normally coming from each phase of the CT with their phase angle. And lower than that, we have this residual current. There are 2 channels available, I01 and I02. The customer can use any one he wants. Here we have a logic of addition or subtraction. It depends upon how you have connected your residual CT. So if there is any fault, we will have a differential current on the calculations that are done here, and they will appear here on this curve is known as characteristic curve. So when you look at simply on this curve, before I explain it further, under this curve, the region is known as restraint region, and over this curve is known as a tripping region. So whatever the addition or summation of the currents appear, that will be plotted on this curve. If it stays in the tripping region, then it will send a command here, where you have an option to trip it or to block it. And also possible that you can make an alarm with the signal. Mostly this protection function does not need to operate immediately because cable end faults are not actually the real faults, but the differential currents start to flow when one of the cable end starts to deteriorate. So most of the customers use this protection function as an alarm signal, so you know that there is something happening in the cable ends, and you do a corrective maintenance before happening a real fault. That's why we call this protection function as a proactive protection function. Here, we will see how the CTs are connected. CT connections can be done in a way that you can see this green part. This is the back of the CT connected in the relay, basically the CT terminal. So you have the 3 phases currents that are connected with the first, second, and third channel of the CT. And then you have I01 and I02 residual channel where you can connect any one of them. But here in the picture, you can see the channel 1 is used for the residual current. Normally, when there is no any differential current flowing, the sum of all currents is 0. And you can see in the plot that the black dots lies near to 0. And there is I sum current. You can see still a summation of current there, means there is a little difference in the CTs, and you can compensate this part by doing this natural compensation in the relay. So you can make it exactly equal to 0 in the curve by doing setting in the relay. So the previous slide, here you see that it's under normal condition, and you can see there is a very little current that flows. That's because of the differential of CT. And now here you have a fault in the rate phase. So when there is a fault, the differential current starts to flow. And if you see in the phasors, there is this I sum phasor. And because of this, in the bias characteristics, you can see that there is 0.5 I differential times current is flowing in it, and it's in the tripping region. So basically, it sends a trip command or an alarm signal, whatever you have set in the settings. This is the Activate software. By using this, we do the settings of the relay. So the interface look like this way when you connect with the relay, and when you are in a live edit mode, there is this protection and stage activation under stage activation, there is this supporting stage. Under the supporting stage, you have I0D mode. When you activate it, this protection functions activates in the relay. Now we will go through the activate software and we will learn how the settings are done. Here we are connected with the relay and we are in a live edit mode. When you go in the protection, stage activation, and supporting stage, you can find this protection function I0D 87N. You make an activation here. In the supporting stage, once you activate it, you can see the protection activate. Now we will go through each tab and see what they mean and what they stand for. Here the first line says that the protection function is activated. Its condition is normal. It's in a normal operating mode. Here you can select restricted earth fault or cable and differential. Our webinar is basically focused on cable and differential, so I will select cable and differential here. When you select this cable and differential, another tabs appear under it known as compensate natural unbalance. So basically here you compensate whatever the differential current is flowing because of the difference in the CTs, the different characteristics of the CTs. And this option works in a way that you are connected with your system with the normal CTs and you can see what is the differential current flowing here because of the difference of CT. And then you press here the compensation. Once you press this compensation, the relay will compensate automatically whatever the differential current is there and it makes to 0. So then the CTs are completely identical now. The characteristic difference is compensated here and now there is no any difference exist anymore and your CTs are completely identical. The reason for doing this is it makes your protection relays very sensitive. Now you can set your relays in a way that a very short differential current can be able to do a tripping and you can sense it. So basically you do not need to compensate this by setting your protection higher after higher values. So you can compensate it here. Now there is this, the second tab says the statistics, where you can see how many times this protection has tripped, blocked, and you can also clear the statistics. Now I just clear it and it will goes to 0. So this is cleared. And then in this tab you have measurements and it's selected primary, secondary or per unit values. You can select whatever you want. Normally it's primary. So you can see primary currents here flowing through each phase and also the residual CT's phase. And then you can also select secondary if you want to see the secondary values and also in per unit. And on the right hand side, here you can see what is the bias current, what is the differential current, and what is the differential current characteristics you have set, and what's the calculated values. And then we go to the settings. In the settings, it says setting group 1 activated. It's also possible that you can do settings in multiple setting groups and you can select any of the setting group you want. But normally we have setting group 1 activated here. Here you have an option to select the channel, that which channel of the residual CT you are using. It can be I01 or I02. By default, it's I01. And currently with the relay, I'm connected with the I01. So I have selected this one. And then you have an option of the add or subtract. You add the values like the 3-phase currents flowing through 3 CTs plus residual CT or minus residual CT. It depends upon how you select according to the direction of the residual CT you have connected. So I make it as a add. And then you have bias current calculation. How you calculate it? There are 2 options. You can calculate it by the mean value or by the maximum value, but it's recommended to use mean value because it's more accurate. And then there are the settings. What is the pickup value setting? Here by default it's set as a 10%, but you can select as you want. And then you have turn point and slope. When we will go through the characteristic curve, I will explain you how these turn point and slope refers to. But basically here, In a journal, I would say that there are two slopes that we are going to set. On the x-axis of this characteristic curve, we have bias current, and on the y-axis, we have the differential current. So basically, we set a number of slopes to have a variety of range of the differential current that we will see in detail when we discuss this characteristic curve. So these are two slopes, and then in the last you have the trip delay, where you can add the delay in your tripping. Normally it's 0 seconds, so I have placed it as 0. So these are the settings that you do normally here in the setting. In the setting tab, it's the same tab that we saw in the info. So it's the same settings here, and in the comment section here you can write some note, whatever you want to write. And then we have registers. In the registers, you can see that what type of event is happened there, what time it happened, and what was the current values there when the event happened, and which setting group used. And there is an option to clear the events. So I clear the all previous events, and now they are cleared. And there are the journal events. They cannot be cleared, but they always stay there, where you can read what had happened previously. This is the input and output section, where you can decide what you want to do when this protection function activates. For example, here I have output 1. So I connect the output 1 of the relay with any of the, it can be with the breaker or it can be with any signal that produce an alarm, and also LED trip. And here in the event section, there are the event mask, where you can decide which events you want to notate. I have selected restricted earthfall trip on and trip off. So I just want to see when the protection function is on and off. You can also select block option if you want. So these are the basic settings that you need to do with the relay. Now we'll go back to the slides. So you have learned how to do the settings, but we will see in the characteristic curve what these settings mean actually. So this is the differential characteristic curve. On the left hand side, you can see what the settings we have done in the relay. So when you have set the turn point 1, at turn point 1, your slope starts to appear, and then you set it as a 10%, and then second slope start at 3 times bias nominal, and it's 40% with the 0 delay. If you see this curve, this characteristic curve, it comprises of 3 parts. I consider this as a part 1, and this slope 1 as a part 2, and this slope as a part 3. So this protection function basically gives us a view from the differential protection that's normally used on a transformer. Basically, it follows the same principle. So this curve is taken from there, and I explain you what each part means. The first part here shows the difference of CT characteristic curve. As I said, when we have the two CTs of the same manufacturer, same rating, we'll have a differential, possible to have a differential characteristic curve. And in a standard 5P class, there is a possibility that maximum it can lead to up to 10% differential current. So this curve starts at a 10% pickup value, so that if there is any differential current flowing because of the difference of CT, should be compensated here. But we know that in the Arcteq relays, this protection function has a capability that you compensate this. You compensate the natural unbalance already. So there is no importance of this part because you have already compensated and CTs are now ideal. There is no differential current there because of the characteristic difference. The second curve here with the slope 1, you see here, this one is the part of tape changer effect. Normally in differential protection, when we use it on a transformer, we normally use the tape changer to compensate the voltage. So when there is a tape changer is changed, there is a differential current. So we compensate that one under this slope. But for this protection function, our protection region is the cable end and there is no such transformer exists. So basically, this part of slope is also not mandatory to be here. And then we have a third slope. This slope is because of the CT saturation. And that's the only part that affects here, that CTs can saturate. If there are two CTs and one of them saturates earlier than the other, then it can produce the differential current. So in order to compensate that, we can use this slope. So it's possible that instead of bringing first two parts, you can make a directly slope of this one with the 40%. That settings can easily be done, and it's settable. You can set, it's a user defined, and you can set whatever you want. And this slope, why this slope is made in such a way that as the bias current increases, there is always higher differential current. So it works in a way that at point 1 of this bias current, the differential current is only 10%. But when we go up at the bias point 5, the differential current is almost 100%. So basically, for a higher bias current, the higher differential current needed to trip this particular protection. What are the benefits of this protection? The benefits, you have already seen it. It's a unique proactive protection function that avoids the flashovers in the cable compartment. It gives easy access that you do not need to have any extra hardware for it. The relays are already there, CT connections are already there, CT wiring is already there. You just need a relay with an active protection function. So no any extra work, extra hardware is needed. And it gives no any extra cost because you're not doing anything extra with it, just using the same wiring and activating this protection function. And it's very sensitive, compensated cable and differential protection that can be used without any extra cost, and it provides additional switchgear and personal safety. This is the data sheet where you can see that for inputs, we have 3-phase currents and then residual current. There are 2 modes, restricted earth fault and cable and differential. And it uses bias differential with 3 settable sections and 2 slopes. And slopes are in different ranges where you can see what should be the range and what should be the stepping size that you can put. And its inaccuracy lies in plus minus 3% when your pickup value is greater than 0.5 times I nominal. And its reset time is less than 40 milliseconds. Let's go to the Omicron testing. Now we have a relay connected with the Omicron, and we will check these 3 conditions to verify how the cable and differential protection works on the real relay. The first condition is the normal situation when we have normal current flowing through the relay, the nominal load. Under the second condition, there is an earth fault, but it's outside the zone. It's not basically a cable end fault. So you will see no differential current or no trip. And third condition, when we have a cable end fault there, and you will see how the relay behaves and what's the differential current. Let's go to the Omicron. Here I'm injecting 3-phase nominal current, and we see that this is the normal situation. There should be no trip. We can see in the relay. Relay is under normal condition. The secondary currents flowing 1 amp through each phase. There is no residual current. And on the right hand side, you can see the bias current and differential current, they are 0. Now we will see the second condition. The second condition says that we are injecting these currents. So basically there is a fault, the earth fault, but it's outside the zone. So cable and differential protection will not do anything. There are other protections. They will activate to tackle this fault. When we see on the relay side, when the fault is outside the zone, there is bias current but no differential current, and here you can see that the calculated I0 and mirrored I0, they are same. So basically, cable and differential is not doing anything, and you can see here it's normal. Now we will verify the third condition. Under this third condition, we have a cable and fault, and we see that in line 1 there is an extra current flowing and there is no residual current there. So it's a cable and fault, and we'll see that how relay behaves. Here you can see that relay in the tripping mode, and statistics shows that there is a one trip happen. There is this differential current. You can see the differential current is 0.16 times nominal, and it's over than the limit. And you can see also here that there are the calculated amps. There is no mirrored I0 current here. So basically, this is the cable and fault, and you can see there is a trip happen. Now you can see in the registers, here you can see that there is a cable and fault happen at this particular time and the date, and you can see what was the bias current, differential current, and then what was the characteristic set and what was the setting group, that the reason for this tripping. And you can also clear from here if you want to clear these registers. Thank you so much for listening this presentation. We have received your questions and we have answered also. If you need more information, you can reach us through the Arcteq support portal by putting up your tickets there. And see you again in the next webinar. Thank you.